Now write the heading D block. D block, F block, coordination. If these three we complete, the entire inorganic will be completed. Okay? Actually, D block elements starts with the scandium. So with atomic number 21, it starts. With atomic number 21, it starts. So like that, it ends with 30. In these elements, 10 elements, if you see, scandium to zinc, there are 10 elements. In all these elements, the 3D sublevel is progressively filled. It starts with the 3D 1, 4s2. So it starts with 3D1, 4s2. Now this 3D2, 4s2. 3D3, 4s2. And chromium 24 has 3D5, 4s1. It is an anomalous configuration, so we put a star mark here. And it is 3D5, 4s2, 3D6, 4s2, 3D7, 4s2. Again, here you have one anomalous situation. 3D10, 4s1. That's why we call this entire row as a 3D series. What this series is called? 3D series. Like that, you have the next series. It starts with yttrium. Zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium. This is called a 4D series. Now here the atomic number starts with 21 plus 18, 39. Here 48. So 39 to 48 atomic numbers, 4D series. The next series is 5D series. Lanthanum, hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold and mercury. This is 5D series. Lanthanum 57 atomic number. But hafnium is not 58, but it is 72. So now the atomic number of zirconium is 40. These two are very good friends. We already discussed in the periodic table lesson. Why they are good friends and why they resemble in many aspects? Because of lanthanoid contraction. Because lanthanum 57, after that cerium 58 to 71 lutetium. These are called lanthanoids. Lanthanum, followers of lanthanum are called lanthanoids because they closely resemble to lanthanum 57. They are called lanthanoids. In lanthanoids, the 4F sublevel is gradually filled. 4F 1 to 14, 5D 0 to 1, 6S2. This is the lanthanoid general configuration. 4F 1 to 14, 5D 0 to 1, 6S2. Now in this, the 4F sublevel is having the peculiar shape or complex shape F orbitals, and these F orbitals cannot have proper shielding effect because of the pore shielding effect of these F orbitals. Pore shielding effect. In lanthanide atoms, there is a gradual decrease in size, which we call lanthanoid contraction. And lanthanoid contraction is over at lutetium 71 because lanthanoid series ends there. Immediately after lutetium, the next element is hafnium 72. So that effect, the decrease in radius, atomic radius, is not only present from lanthanum to lutetium, it also falls on the next element, hafnium. That's why zirconium and hafnium have same radius. Actually, in a group, down the group, the atomic radius should increase. But zirconium and hafnium have similar atomic radii due to lanthanoid contraction. There is one more anomalous situation here. In zirconium nucleus, there are 40 protons. Atomic number is 40. In hafnium nucleus, 72 protons. So though they have similar size, here 40 protons, here 72 protons. The last electron is pulled by 40 protons here. The last electron is pulled by 72 protons here. Both are having same radius. So the nuclear pull is more in which case? In hafnium when compared to zirconium. The hafnium nucleus will have a greater pull over the outermost electron. That's why to remove this electron, more ionization energy is required. than here. So if you compare the ionization energies, IE, ionization energy of hafnium is greater than IE of zirconium. This is also an anomalous situation. Actually, down the group, the ionization energy should decrease. But when compared to 4D, 5D series of elements, all these elements will have more ionization energies than the 4D. So you can generalize and say IE of 5D is greater than IE of 4D. 4D series. The second important point, just now we discussed, atomic radius of 4D and 5D are similar. This is one more important consequence of lanthanoid contraction. Now one more point, actually, if you take any group, suppose you take manganese group, what are the elements? Manganese, technetium, rhenium. Or if you take chromium group, chromium, molybdenum, tungsten, this is one group. Actually, the elements of a group should resemble with each other, definitely, because of similar valency electronic configuration or similar outer configuration. The elements of a group resemble with each other. But here the resemblance between 4D and 5D is more than 3D. That is the third consequence of lanthanoid contraction. One here, two here, third. What is the third consequence? The resemblance of or the similarities 4D and 5D is more than 3D and 4D. So, if a statement type question is asked, how many of the following are true statements? Suppose is the first statement, zirconium and hafnium have similar atomic radii, correct. The similarity in atomic radii of 4D and 5D is due to lanthanoid contraction, correct. The ionization energy of 5D is greater than 4D, correct. The resemblance of 4D and 5D are much more closer than 3D and 4D, correct. So this type of statement type questions. Now, the second or the last one is 6D series. Actually, in 6D series, you have actinium, thorium, actinium, actually actinium 2, 103, lawrencium, 89 to 103. These are called actinoids. Lanthanoids, actinoids. In actinoids, the 5F sublevel is filled. In lanthanides, 4F is filled. So 6D 0 to 1. 7s2. So 104, I think, please refer your text also, Rutherfordium. Correct? I think next one is Dubnium. Dubnium Db. Next is Seaborgium Sg. Next is, I think, Borium. Please refer. So here 89, but it is not 90, it is 104, 105, 106, 107. I think next one is empty. Hassium metrinium. Okay, hafnium. Next is metrinium. Next is Dom Stadium. DS or DT? DS. Röntgenium, RG. Röntgen means who discovered X-rays. You have studied in your 8th class or 7th class. X-rays were discovered by Röntgen. 110, 111. Next, Copernicium. KN, CN. Okay. (112). This is the entire series 6D. So total 3D, 10 elements, 4D, 10 elements, 5D, 6D, total 40 elements. The entire D block contains 40 elements, all are metals. All D block elements are metals, which are hard with high melting points, contrary to the S block metals, which are very soft with low melting points. So comparative melting points, comparative hardness, if you take the melting and hardness, melting points and hardness of D block elements is greater than S block elements. Why? Why? The answer is very simple. Both hardness and melting point depends on the metallic bond strength. The strength of metallic bond is more in D block elements than in S block elements. So why? You may ask why? Why the metallic bonds are stronger here in D block? Why they are weaker in S block? So metallic bond strength depends on how many valency electrons participate in metallic bonding. In S block, only two groups are there, first group and second group. In first group, you have only one valency electron, which can participate in metallic bonding. In second group, only two valency electrons. So in the entire S block, the number of valency electrons that are participating towards metallic bonding are very less. That's why they form weak metallic bonds. That's why they are very soft metals. They easily melt. Even potassium, rubidium, cesium melt at 30 degrees centigrade temperature. Your body temperature, they melt. And but in D block, the number of valency electrons are more in participating metallic bonding. And also, comparatively, their sizes, atomic sizes are small. So, strength of metallic bond depends on two factors. Strength of metallic bond. Directly proportional to number of valency electrons. Directly proportional to directly proportional to number of valence electrons. White is not selected. So number of valence electrons inversely proportional to, write one more point, inversely proportional to which one? Oh, maybe.
So you can write.
Yes. Now it is selected as. So strength of metallic bond. Again, I am repeating. Directly proportional to number of valence electrons and inversely proportional to size of metal atoms. Based on this, please refer your textbook. If you look at the textbook, there is a melting point curve. So on one axis we take melting point, on other axis atomic number Z. If you take the 3D series, the curve follows like this: scandium, titanium, vanadium, chromium. After chromium, suddenly at manganese, the melting point decreases. This they will ask you as a question. After manganese, again iron, cobalt, nickel, copper, zinc. They ask this point or this point, zinc. So why the melting point curve suddenly shows a deflection at manganese? Up to chromium it increased. Suddenly at manganese it has fallen. Of course, zinc also showing very low melting point. The reason is very simple. In manganese, there is a half-filled orbital configuration. The 3d5, if d sublevel is filled with 5 electrons, we call it as half-filled orbitals. S sublevel is 2 electrons fully filled. This is a stable configuration. That's why the electrons of manganese, due to their stable configuration, they are not actively involved in metallic bonding. Those 7 electrons are there. All 7 are not willing to effectively participate in metallic bonding because they are already having a stable configuration. That's why since number of valence electrons participating in metallic bonding is less, melting point suddenly fallen. And zinc also 3d10, 4s2. So that's the reason in the 3D series, 2 elements are showing sudden change in their melting points. That is, one is manganese, the other is zinc, because of their stable configurations and the electrons are not participating in metallic bonding. This is one important point from your textbook. We have to be very careful. Similarly, from your textbook, one more graph also you have to notice. This graph. Atomic radius versus atomic number. Actually, left to right, the atomic radius must increase. Increase or decrease? It should decrease, sorry. So, look at so this is scandium, titanium, vanadium, chromium, nickel, copper. At zinc, there is a slight increase. Almost from chromium to copper, the radius is almost similar. So as the atomic number increases, the atomic radius should decrease. But up to scandium to chromium, it shows a slight decrease. From chromium to copper, it almost remains constant. At zinc, there is a slight increase. So actual periodic trend is left to right, the atomic radius should decrease. But why it started initially decreasing? Why it remains as a constant for many elements? Why in the case of last element, the radius are here 4s2 electrons are there and 3d is gradually filled. So the newly occupying electrons are in the 3d, which is not in the outermost shell but penultimate shell. So in the entire D block, which subshell is filled? You have to say the D subshell of the penultimate shell. Penultimate shell means n-1 D shell. The last shell is called nth shell. So the shell prior to nth shell, the last but one shell, is called penultimate shell. Here the electrons are filling, or the electrons are occupied in this. So here nucleus is there. When the nucleus want to attract the outermost electrons, that is 4s electrons, the newly occupying electrons of the 3D sublevel, they cause certain amount of screening effect or shielding effect. They say, my dear nucleus, why are you more worried about 4s? We are very nearer to you. Fourth shell, and compared to fourth shell, third shell, we are nearer to you. And they don't allow the nucleus to pull these 4s electrons. They cause shielding effect or screening effect. So because of the screening or shielding effect, the nucleus cannot pull these outermost electrons. Whenever nucleus is unable to pull the outermost electrons, the size won't contract. That's why the size almost remains constant. But why at zinc the size suddenly increased? In case of zinc, the 3D10 orbitals are completely filled. 4s2, that is also filled. Between filled electrons and filled electrons, repulsions arise. The shells move away from each other. That's why zinc, there is a sudden slight increase. So why the atomic radius of zinc is more than cadmium, the previous element? Not cadmium, copper. Copper is 29 and zinc is 30 atomic number. So why when compared to copper, the atomic radius of zinc is higher? The answer is due to repulsions between the completely filled orbitals. Why the atomic radius from chromium to copper remains constant? Due to shielding effect of n-1d electrons, which prevent the nucleus to pull the outermost electrons. Now if you look at, this is 3D series, and if you draw a similar diagram, okay, if you draw one more diagram, or one more graph between atomic radius versus atomic number. Now this is for 4D and 5D. Forty means from yttrium, zirconium, niobium, tantalum, tungsten, rhenium, like this. Actually, these two curves are almost merging with each other. You can see from your diagram. Why 4D and 5D series of elements, their atomic radius curves are meeting with each other due to lanthanoid contraction? Why these two curves run parallel to each other? Almost they are meeting with each other due to lanthanoid contraction. So from NCERT text, graph-based questions in D block are these melting point curves and also atomic radius curves. Now coming back to The next point, general characteristics of D block. General characteristics of D block. In this, first you write variable oxidation states. Variable oxidation states. What is meant by variable oxidation states? Showing different oxidation states due to the participation of unpaired electrons of the n-1d subshell along with ns2 electrons. Along with ns2 electrons. Suppose the directly question is asked, what is the reason for why D block elements are showing different oxidation states? Because different electrons are participating. What are those different electrons? The unpaired electrons of n-1d subshell, along with, if only ns2 electrons are, outermost ns2 are participating, they show +2 oxidation state. That's why the common oxidation state, the common oxidation state of D block is +2. The common oxidation state is +2. Now we'll take one particular example and see how the oxidation states vary. So that is, I take scandium 3d14s2. All three electrons participate here. Shows only +3 state. No other oxidation states. Because scandium is 21 atomic number. If 21 electrons of scandium 3d14s2, if it loses 3 electrons and becomes scandium 3+ ion, it acquires stable argon configuration. Why scandium is not willing to show other variable oxidation states? The answer is because at a stretch it wants to lose 3 electrons. You don't want to exhibit other oxidation states, because by losing 3 electrons, 21 minus 3, 18 electrons. 18 electrons is the argon configuration. Thus, which D block element or elements do not show variable oxidation states? Which not D block, which 3D series? In D block, which elements of 3D series do not exhibit variable oxidation states? or which pair of 3D. I can just alter this. Which are the following pairs of elements in 3D series do not exhibit variable oxidation states? The answer is the first element, and the last element is zinc. We will see that also. If you take titanium, 3D2,4s2. The possible oxidation states, if 2 electrons participate, it will show +2. 2 s electrons and 1 d electron, it can show +3. 2 s electrons and 2 d electrons. So titanium can show how many oxidation states? 3 oxidation states. +2 if only outer 2 s electrons participates. +3 2 outer s electrons and 1 d electron participate in bonding. +4 if all 4 involved in bonding. That's why you have titanium dioxide. What is the oxidation state here? +4. You have +3 also. Titanium chloride. In +3 state of titanium, how many electrons are left? 1 d electron is left. In +3 state, it is 3d1, 4s0. This 1 d electron of titanium occupies in one of the d orbitals. You have 5 d orbitals: dxy, dyz, dzx, dx square, y square, dz square. All are having equal energy. We take energy axis. But when titanium ion, when it is present in aqueous medium or in the form of a salt, the d orbitals split into 2 categories. These 3 become one set, these 2 become another set. And this is the lower energy set, this is a higher energy set. So we call it as dx square, y square, and dz square. This is a higher energy set, and this is called EG set. The remaining 3, dxy, dyz, dzx, this is T2G. Now the single electron definitely occupies the lower energy T2G set. Correct or not? Electrons always want to occupy the lower energy orbitals. That is the Aufbau principle. Now this electron absorbs in the visible light, in the VIBGR, the green color wavelength, its lambda is equal to 500 nanometers. So the single electron of titanium absorbs which wavelength of light? The green wavelength of light, and jumps into T2G set, EG set. This is called a D to D transition. What we call? DD transition. Again I repeat, titanium in +3 state has only one unpaired electron that occupies the lower energy T2G set. But this electron, whether it is in the form of a salt or when it is in aqueous medium, the single electron of titanium absorbs the green light whose wavelength is 500 nanometers, or angstroms 5000 angstroms, and jump into another set of d orbitals called EG set of orbitals. So T2G set to EG set, one kind of d orbitals to another kind of d orbitals. This is called a DD transition. Actually, when all these 7 colors of light is present, we call it as white light. So in white light, which is absorbed now? Green is absorbed. Green is absorbed by single electron of titanium plus 3 ion in the form of a salt or in aqueous medium, or this one. Now, how many wavelengths are left? These 6 wavelengths appear in the form of purple color. So why titanium salts are purple colored? The answer is because of the absorption of the green light from the visible region. And the electron undergoes DD transition. Means here I am explaining the color exhibited by most of the D block metal ions in aqueous medium or in the form of salts. So D block elements are metals. Metals are not colored. Mostly metals are bright metallic luster. Some metals like gold is an yellow color metal. Copper is a red metal. Silver is a white metal. But silver, aluminum looks almost similar. But silver has its own finishing. Platinum is also silvery metal. Mostly white metals, except copper and gold, red and yellow. Why metals are lustrous? Again, metals have free electrons called electron C. This electron C also absorb light from the visible region, and the electrons get excited. This excitation, how much energy they are absorbing from the visible light, that gives the color of the metal. Actually, aluminum is we say white metal, but it's a bluish white metal. It is not silvery white, it is bluish white. But we can't see that blue color. Okay. Now, here in the variable oxidation states itself, we are studying one more common property exhibited by D block elements, that is color. So what is the color of titanium 3 plus? In aqueous medium? Purple. Why purple color? Because it absorbs green color light from the visible region. And the remaining 6 wavelengths in the VIBGYOR, when green is absorbed, the remaining 6 wavelengths appear in the form of different color. It is called a complementary color. Called complementary color. In a nutshell, you should know that the color exhibited by D block elements is due to 2 factors. One is due to the presence of unpaired D electrons. The second is these unpaired D electrons absorb. Please wake up that doctor, operation is going on. Okay. Regarding you, we have also a WhatsApp group. And I came to know that happy news that you are scoring marks like anything. Like rocket speed you are traveling. And among the group members, they are congratulating each other that we are going to get a wonderful result. And in this particular test, I think the previous test, someone has touched 600 mark. Who is that? $600. 500 marks, how many? After 600, we are coming down to 500. Oh, 550? No. 450? 453. Okay, good. Definitely, you have a lot of time. 5 months' time is there. You can make up. Moreover, day by day you are strengthening. Concepts are becoming more and more clear. So in the real scenario, the number of silly mistakes that you commit will also become less. The only thing you have to do, many tests are over. Make a big file and write explanations for the questions also. And how many questions you did wrong. If the same question is asked, whether you are again going to do wrong or right. That is called mistake analysis. Generally, in our scenario, we only do why we have done mistake and do analysis for that. But in some foreign universities, why it is correct also they do analysis. Generally, if we do correct, we will happy, we don't touch also. We don't look at it also. When you do a question right, take it for granted it is right, you are happy, and you never bother about why it is right. But there are some institutions, they thoroughly do research why it is right, why it do not go wrong. That is even advanced stage, that one. Okay, coming back, okay, you are doing good, that is a wonderful thing. Because we want to see most of you as doctors. That is our aim, your Meghalaya government aim, your parents' aim, and your aim also. We are all fighting for a common cause, that you have to become doctors. Because why we get an advantage out of this? Yesterday, 2-3 days back, I received a WhatsApp video thing. One actress, she's an actress, and her father, she's a Hindi actress, I think, and her father is a famous cardiologist. And the daughter is interviewing her father. She's asking, what about these lipids, cholesterol and all? Are these linked to heart attacks and all these? And he is a famous cardiologist. He is telling that, no, cholesterol is made in the body, not you are eating more oily food, you have more cholesterol, you are using more butter or ghee, you have more cholesterol. Or some people are eating more non-vegetarian, cholesterol levels will increase. He is saying that it is all a myth. Cholesterol is made within the body. It is required for protecting your myelin sheath around the nerves. It is also an immune booster. Like that, he is telling a lot of uses of cholesterol. And he also said, I will give one data. You will wonder, my cholesterol is now 375, like that he is telling. But generally, if you go to a doctor, if 200 is cholesterol, he will put a tablet to lower the cholesterol. They are called statins, atorvastatin, rosuvastatins. Statins are blood cholesterol lowering agents. So the doctor brand you as hyperlipidemia. Hyper means more, lipids are more. Hyperlipidemia. See, even I heard this type of discussion long back by the American papers, American scientific papers, also saying there is no link between the heart attacks and cholesterol. And this entire usage of statins is a big fraud in medical history. So immediately I forwarded the same to one of my students, Dr. Vikram, who is a very good physician working in Dubai. Dear Vikram, you find it, whether it is a fake video or something is true in this. Immediately he replied within half an hour. He is telling that whatever he is saying is correct only, to my knowledge. He also uses that word. And he gave that answer, whatever he is saying is correct. But he also mentioned statins definitely lower the cholesterol. I think he is not satisfied with his answer. Immediately he contacted one of his friend. She is a cardiologist. And she sent me one audio message in our language. She is telling that definitely cholesterol, lipids are flowing through the blood. All that lipids are not attached inside the wall of the artery. They are flowing, no doubt, what he is saying is correct. But due to some genetical factors, some other factors, in some people, they are deposited on the inner walls of the arteries. That may cause heart attack. So usage of statins, blood cholesterol lowering agents, should be well judged by the doctor, whether he is having any family history of heart attacks. So a lot of things he has to study and prescribe statins. Not simply, but mostly our Indian doctors, cardiologists, American doctors, everybody, they will see the blood report. Oh, your cholesterols are very high. Take this tablet at bedtime. And this cardiologist, that actor's father, is telling, cholesterol levels differ from season to season. In summer they are high, in winter they are low. We don't know all these things. And during infections, their levels will fall. Due to usage of some antibiotic, they rise. So many fluctuations. Cholesterol levels, lipid levels. So actually this type of things we better understand through our students only. So that is our advantage. Not that you come and treat me freely. There are many doctors, number of doctors available in corporate sector. Just book an appointment. It is not America. In America you don't get a doctor. If you book an appointment, you will give it 3 months after. So American healthcare system is very bad. Doctors are not available. If you have urgency, go to emergency room, they will tell. They call it as ER, emergency room. Emergency room charges are very high. That's why people are worried to go to emergency room. Then if they directly want to meet a doctor, only after 2 months, 3 months. Very rare doctor visibility. Saturday, Sunday, they are not at all visible. So after +3, +4, +5. Because 2 s electrons, it will show +2. 2 + 1 combination. 2 from S, 1 electron from D. 2 + 2 combination, the oxidation state will be +4. 2 from 4S, 2 from 3D. 2 + 3 combination, 2 s electrons and 3 d electrons. All 5 involved. The maximum oxidation state of Vanadium is +5. That you have studied V2O5. Vanadium pentoxide. V2O5 is a catalyst in contact process for the manufacture of sulfuric acid. V2O5 is a very well-known compound. Vanadium pentoxide. Now if you come to chromium, 3D5 4S1. But it won't show +1. So only one s electron can participate now. So chromium can show +2, +3, +4, +5, +6. CrCl3. Chromium shows +3. Cr2O3. Chromium trioxide +3. Cr2SO4 thrice +3. CrNH3 6 times. Cl3. CrNH3 6 times. Cl3. Hexamine chromium 3 chloride. What is the IUPAC name? Hexamine. Amine spelling AMMINE. Hexamine chromium within bracket Roman number 3 chloride. It is a chromium complex. Mostly they are attracted by light and they die because of the heat of the light. Now +6, potassium dichromate, potassium chromate, K2CrO4, chromium peroxide, CrO5. So chromium can show maximum oxidation state +6 in all these three compounds. It is orange color dichromate, it is yellow color, it is beautiful blue color. They use that word because we have many blues like Turnbull's blue, Prussian blue, Turnbull's blue. They are all blue different shades. This chromium peroxide they mention in the chemistry textual language as a beautiful blue. So in all these, chromium has no unpaired electrons. Whether you take potassium dichromate orange color, or when you take potassium chromate yellow color, or if you take chromium peroxide blue color, in all these three, chromium is in +6 state. +6 state means all these electrons are gone. 3D0, 4S0. But actually color is due to unpaired d electrons. One of the prime reasons for color exhibited by the salts of d block elements is due to unpaired electrons. But here there is no unpaired electron in +6 state, yet they are colored due to charge transfer spectra. Write that point, most important. K2Cr2O7 orange, K2CrO4 light yellow, CrO5 blue color. These are all colored due to charge transfer. The charge transfer from the ligand to metal or bonded atom to metal. The charge transfer is due to ligand to metal L to M. Or bonded atom to metal. I'll explain with one example. This is CrO4 2 minus. This is called chromate ion. In chromate ion, this chromium is in which state? In +6 state, it has vacant orbitals. Vacant orbitals. Now the charge, negative charge on the bonded atom is transferred to the vacant orbital. Negative charge transferring. From whom to whom? From the ligand to metal or bonded atom to metal. This charge transfer also requires certain energy. That energy is absorbed from the visible region. So this charge transfer from ligand to metal, L to M, is responsible for the colors of dichromate orange, chromate yellow, and chromium peroxide blue. Similarly, after chromium, you take the example of manganese. With 3d5, 4s2. As usual, it can exhibit +2 if only 2 s electrons are involved in bonding, like MnCl2. But it can also show +3, +4, +5, +6, +7. +6, K2MnO4, potassium manganate, dark green. KMnO4 +7, violet color or pink color. So here it is +6. In +6 you have one unpaired electron. Why KMnO4 is a pink color with no unpaired electrons? With no unpaired d electrons. The answer is due to charge transfer only. This is MnO4 minus. Permanganate ion. Charge transfer from where to where? Ligand to metal only. So MnO4 minus is pink color for potassium permanganate. Suppose I can link one question here. Directly you have to answer. Permanganate is titrated with oxalic acid in acidic medium. What is the equivalent weight of permanganate? Or what is the N factor? KMnO4 versus oxalic acid. Potassium permanganate versus oxalic acid in acidic medium. We are titrating. So the pink color of permanganate is decolorized. So in this titration, what is the N factor per permanganate? Or what is the equivalent weight of permanganate? Okay. So MnO4 minus in acidic medium converts into Mn2 plus. So plus 7 to plus 2. It is a 5 electron change. If you add 5 electrons to plus 7, it becomes plus 2. Means it is taking 5 electrons to convert into plus 2. The one which accepts electrons is an oxidizing agent and undergoes reduction. So here the N factor is 5, or the equivalent weight of KMnO4 is equal to molecular weight by 5. Very standard, like sun rises in the east. You should not take time or you should not expect me to answer this. A very standard question. In alkaline and neutral medium, what is the N factor for permanganate? In alkaline or neutral medium, permanganate is always converted into manganese dioxide. So plus 7 to plus 4. So 3 electron change. N factor is 3. What is the N factor when potassium dichromate is titrated in acidic medium? Very good. So K2Cr2O7 in acidic medium converts into chromium 3 plus. So plus 6 to plus 3. It is a 3 electron change actually. But for 2 chromiums, 2 into 3 electrons, 6 electron change. So equivalent weight of dichromate is equal to m by 6. So in 3D series, now we have started from scandium, titanium, vanadium, chromium, and we reached up to manganese. Now you can generalize a point here. After manganese, the ability to show higher oxidation state, decreases due to the pairing of d electrons, So after manganese, the next element is iron, 3d6 4s2. So what is iron? 3d6 4s2. It shows not +2 to +8. It only shows +2 to +6 maximum. After iron, next is cobalt, 27. 3d7 4s2. What is the oxidation state range? +2 to +5 only. After cobalt, nickel, 3d8 4s2. What is the oxidation state range? +2 to +4 only. After nickel, copper, 3d10 4s1. It shows +1 and +2. It shows +1 and +2. The last element is zinc in 3D series, 3d10 4s2. It only shows +2. No variable oxidation states. So how many elements in the 3D series do not show variable states? The first element scandium, the last element zinc. Remaining elements show variable oxidation states. Why? Why they show? Because of participation of unpaired d electrons along with outer ns electrons.